Hello and welcome to Solids of Revolution. Yay! Alright, my name is Zach Flagel, and I'll be teaching you all about Solids of Revolution. Thanks. Alright, so today we're going to approach Solids of Revolution and forming those and seeing all the cool things about them. Alright? So, in my book, there's two ways to approach Solids of Revolution, right? There's one way where you approach it visually and graphically, and then the other way you approach it mathematically through equations and whatnot, alright? So first I'm going to show you how to approach it through the visual graphical method, alright? So let's say we got a graph right here, alright? Now, the way you approach it visually is that pretend that we're going to make a cup, alright? We're going to make a cup, and we are going to use y equals square root of x in that equation. So it follows something like this, alright? And this is y equals square root of x, right? Now, the solids of revolution, we're going to have to make a revolution all the way around, let's say this x-axis, right? It could be over the x-axis, or it could be over the y-axis. Or a different axis that doesn't have to be a certain one of these two. It could be over x equals 3 or y equals 2, whatever axis we want to make. But for simplicity's sake, we're going to use the x-axis for the first example. Alright? Now, we're trying to make a cup, a little teacup, right? And so, I'm going to go like that, right? Now, this is completely revolutionized. Right? So imagine right here, this is the top, and that's the bottom right there, right? So you see if we turn it on its side, it looks like a little teacup, alright? Now, this is just using the equation y equals square root of x and rotating it all the way around the x-axis. So if you can imagine the part that I just shaded in a little bit, that part is like the surface, and here would be like a hollow hole, should we want that to be. Alright? Now, if let's say we're looking at the radius, right? And we're trying to see what is the radius of a certain point. Let's say right here, right? Let's say this would be the maximum radius of the circle, of the large circle of the opening top, right? Well, we know that y equals radical x. That's our equation. So all we have to do is find this x value right there and plug it into the equation, and we get whatever point right there is. Alright? And there we find the radius of the circle, and that works certainly well for any point. You want to find the radius right here, go ahead, you just plug in that x value and you find it. Right there, same thing, anywhere you want, that's how you find the radius. Now, to use this radius to find the volume of the solid of revolution, we must think about it from a perspective of what actually is volume. Volume is length times width times height, or with circular objects such as this, the area of the circle projected across a certain depth. Alright? And so the area of this circle projected across a certain depth would be V equals pi r squared times the depth, right? Now, we have pi. R squared, well, r is forever changing, corresponding to the certain y value where the radical of x is, wherever on the certain line, right? And so, another way to write the radius in this certain problem is f of x. And you square that because pi r squared would give you the area of the circle, right? And then times a certain depth of x. So pi r squared dx, right? And when applied to a certain drawing over point A to B, we must take the integral of this. So you take the integral from the definite integral from a to b, and you have your d of x already. So essentially, this is the way you solve the problem from the visual graph point of view. So now we're going to try to solve this equation, this finding the volume of this figure through the mathematical equation way, right? And so we're given this. We know that the volume of a certain figure as this is the integral, the definite integral of the area of the circles, right? And the areas, it's always changing, right, from point A to point B, right? And so we have to take account for that, and I'll show you how, right? And so let's pretend that point A is 0, right? And point B, let's say, is 4, all right? And so volume equals pi from 0 to 4, from A to B, right? R squared, so R is obviously radical x, right? So x to the 1/2, that squared dx, right? So you get the pi r squared, and you're taking the definite integral from 0 to 4, right? And so if you want me to do the next part of the equation, this simplifies to x, right? And so take the integral of that, you get 1/2 x squared, right, from 0 to 4, right? And then just plug in 4 minus 0, right? You take the easy integral, everyone knows how to do this, and you end up with 8 pi, and that's how you do it. End up with 8 pi, and that's basically how you solve the equation from a mathematical perspective. And this is one of the more simpler problems. I'll show you one more example right now that's a little more challenging, and it uses a little bit more thinking from the mathematical perspective. Alright, we're back, and we're going to try to attempt to solve a problem that's a little bit more challenging, but still on the easier side of things. Alright, and it is find the volume of the solid bounded by the graph of f of x equals radical sine x and the x-axis from 0 to pi. Alright, so basically the graph of radical sine x looks a bit like this, right? So this is y equals radical sine of x, and we're going to rotate it over the x-axis, right? And so we're going to rotate it this way, and it's going to look about like that. So it's going to form what I would consider, an egg shape, per se. And it's going to be from 0 to pi, as stated in the problem. Alright? And so we're going to approach this from the mathematical perspective. Alright? We already have v equals the equation that we are always given, the formula, from a to b, or from 0 to pi, as given in the problem, of the radius squared dx, right? And so, just to fill in a couple things, the radius would be radical sine x, and that would be squared, so basically it's just sine of x. So we got this so far. Alright? So the next step of the problem is to actually integrate it, right? And everybody can do this, but I'll do it just for the sake of it. Alright? So it simplifies to this. As you can see, the integral of sine of x is negative cosine of x. So you got the negative cosine of x, pi from the front, and then you just have to finish off the integral by plugging pi and 0 into it. Alright, and this simplifies down to negative pi times cosine of pi minus cosine of 0, or when you do the math, it goes down to 2 pi, which is your answer. Alright? Good. To end my presentation, I'd like to just talk about a little bit about the practical uses that we can see the solids of revolution in real everyday life. All right. The first area that we can talk about, obviously, is the engineering that we see of like the certain cups or the certain bowls or the certain any kind of object has to be engineered at least at its inception, right? And so like cups such as the one from the first problem that we did just followed simple equations that we plug into a computer, that engineers plug into a computer and pass on to machines, and that they follow these equations to make, right? And so it's useful. I know in my engineering class I took sophomore year, we used a program called Autodesk Inventor that dealt precisely with making objects such as these and using equations and certain visual representations to find the volume and surface area and other measurement tools of certain objects, right? And that brings me to my second point. Another practical use that definitely the equations and the formulas for surface area and volume of revolutions helps us with is actually finding the actual volumes of like actual everyday items, like drinking out of a cup. Well, we might not have the equation there. We certainly have the tools necessary should we find that equation or see areas in real life where this actually applies to, and we would be able to find the surface area or find the volume of these certain cups that we see in everyday life. They're all around us. Everything is, as I said, was had to be engineered to a certain point, and it all starts with the solids of revolution. So that's it. That's my presentation. I hope everyone liked it. I hope you learned a lot. And if there's anything else I can do to answer questions or clarify anything, please don't hesitate to get me. All right, thanks.